So we've seen forces, linear forces acting on an object, and we've seen that we can cause objects to move translationally, so we can move them up and down, left and right, forwards, backwards, or whatever direction we want. But what happens then if we've got forces that are causing an object to rotate instead? So instead of going forwards, backwards, up and down, it's rotating clockwise or anti-clockwise. Now, in order for that to happen, we need to have what's called a pivot. Okay, so in this case here, I've got a spanner that's going to try and turn this nut, or this bolt. So the pivot, you can see, is going to be about there, right in the middle there. So that's my pivot. Okay, so the pivot is the fixed point about which the whole system is going to rotate. So if I apply a force then, here, the whole system is going to rotate about the pivot. So it's going to rotate in this direction, which is anti-clockwise. And this is what's called our moment, okay, or our moment of a force. Okay, and in this case, it's anti-clockwise. So it has got a direction associated with it. Therefore, it's a vector quantity, okay, because it's got a magnitude and a direction. Now, what else does it depend on? So if we had a longer spanner, you could probably know that if you had a longer spanner, it's easier to turn the bolt. So it also depends on our distance to the pivot. Now, specifically, it's our perpendicular distance to the pivot, and it's perpendicular to the force. Yeah, so perpendicular to the force. So it's going to be this distance here. Okay, so distance to pivot perpendicular to the force. That's quite a mouthful, that. So I'll clarify that slightly more. So, for example, if I changed the direction, or if I changed the angle of the force, in this case, if I change the angle now to this angle, okay, now it's perpendicular. Now the distance that I'm going to use is going to be perpendicular. And it's going to be perpendicular to the force, which is going to be this distance. Yeah. Notice that this distance here is significantly smaller than this distance here. Yeah. So it's essentially like turning a shorter spanner. Now the equation that we can use to relate these things together, we take the moment, and in order to calculate the moment, we take the force, and we multiply it by that distance. Okay, so we take the force, we multiply it by the distance. Force is measured in newtons, of course. Distance is measured in meters, of course. Therefore, moment is Newton times meters, which is Newton meters. There we go. So there's our equation. And this is an equation that you need to remember as well in the AQA spec. Okay, right, let's have a look at some more complicated situations then. So this is a case then when we've got two moments acting on a system. So we've got two rotational forces acting on a system. We've got the blue forces, and we've got the blue distance and the blue force, and we've got the orange distance and the orange force, which we need to find out in this case. So how do we approach a problem like this? So something you need to know is the law of moments. Okay, just like forces, if you've got two forces in balance, if you've got two forces in equilibrium, then it's going to be balanced. There's going to be no acceleration. In this case, if there is two rotational forces or two moments in balance, then there's going to be no rotation here. Okay, so let's write that out. So if it's the clockwise moment, so in this case, the clockwise moment is going to be provided by the orange stuff, so the orange distance and the orange force. And we're going to say if it equals the anti-clockwise moment. In our case, our anti-clockwise moment is produced by the 6 meter distance and the 10 Newton force, the blue stuff. So if the clockwise moment equals the anti-clockwise moment, if they are the same, so the same magnitude in opposite directions, then they are going to balance. They're going to be in equilibrium. In this case, there's going to be no rotation of the system. Okay, so no rotation will occur. Right, so firstly then, we got to work out the anti-clockwise moment. We can find out the anti-clockwise moment just by taking 6 newtons and then multiplying it by 6 meters and multiplying it by 10 newtons. And that's going to produce a moment in this direction, the anti-clockwise direction. So that's going to be 60 Newton meters. Now 60 Newton meters, so we've got to make this moment on this side, the clockwise moment, has to equal 60 Newton meters. So it's 3 multiplied by the force, which we don't know yet, is going to equal 60. Okay, so 60 divided by 3, that's going to give you 20 newtons of force. Okay, so this force here, this linear force, has to equal 20 newtons in order for the system to balance, because 20 times 3 is equal to 60, and 10 times 6 is also equal to 60, so it's in balance. Now let's have a look at a slightly more complicated situation. Well, it's actually not any more complicated, it just looks more complicated. But we've just got to figure out, so we've got two forces here. We've got a 600 Newton force acting this way, and this is going to try to produce an anti-clockwise moment this way on this log here. And then we've got a rope tied to the other end of the log that's going to try and produce a clockwise moment that way. And we're going to try and figure out what force is required to keep this log in balance. So we've got it. So we've got the log resting on top of this pivot here. So everything is going to be pivoting about this point here. Right, so firstly, we know how to calculate the anti-clockwise moments because we've been given both 1.5 and 600. So if we just take 1.5 and times it by 600, we get a moment of 900 Newton meters. Okay, so that's the anti-clockwise moment. What about the clockwise moment then? So how do we calculate the clockwise moment? So we have to take the question mark, the force, and we multiply it by 3.5, and that has to give us 900, because remember, moment on the left equals the moment on the right, or the anti-clockwise moment equals the clockwise moment, and the anti-clockwise moment is 900, so the anti-clockwise moment also has to equal 900. So take 900, divide it by 3.5, and you get 180 newtons of force. Okay. Right, so these ones are more tricky. I am going to put some questions below on a sheet for you guys to have a go at. I'll put the answers down there as well. See how you get on, and I'll see you in the next video.